All right, welcome. In this video, I want to follow up on what I was talking about last video, where we did some collision detection between these circles and collision handling to make sure they bounce properly and they don't overlap and occupy the same space. But now I want to go into just basically the physics or the behavior behind the agents actually playing tag. So here I've got them sort of simulating this game of tag. How did I build in that behavior? In fact, the behavior I've built in is in fact very simple. I've got it built in with just a few lines of code over here, and that's because what I'm actually doing here is a physical simulation. I'm simulating physical attraction as though these entities were, planets attracted to each other with gravity, or these were maybe electromagnetic, particles like electrons and protons that are attracted to each other through an electromagnetic attraction or pull. Now those forces are forces of the physical world, and often by simulating those forces in the simulated world or in a virtual world, we can get things that kind of look realistic. So this kind of looks like it might be, some children or robots maybe playing tag in an environment. It kind of looks realistic, even though, and this is the cool part, underneath is very, very simple rules. So let's take a look at some of those simple rules. All right, so imagine we're it. We're the entity that's it. And what we want to do is we want to figure out how we should move or attract our movement towards our targets, which are these other circles that we see. Now, for the moment, I'm going to just consider one circle. Let's say that this is the target that we want to move to. If it is, the first thing we're going to do is we're going to use our two coordinates here, which are our center points of our two circles. And again, as we did in the last video, I might call these x0 and y0 and x1 and y1. And what we're interested in is the difference vector between these two, which is going to be x1 minus x0 and y1 minus y0. This vector that we calculate here this difference vector will be this direction, or this vector that's going in this direction. This is the vector that we would want to add to this vector, our current position, if we wanted to eventually be at this position. Okay, so we're currently at this position. We want to be at this position. How do we get there? We have to add this vector on, and that probably makes sense. You can probably see if we added x0 into this vector, the first coordinate will be x1, and if we add y0 into this vector, the second coordinate will be y1. So exactly what we want. So one thing we could do here is we could actually set our velocity to be this vector. Now, if our velocity is in pixels per second, that would mean what we would be doing there is setting ourselves so we would arrive at our target location in 1 second. Now that's not exactly what we want to do. It's a possibility. You might want to do that. What I want to do is instead accelerate towards my target. So I want to act as though I am being attracted towards my target. So that means I need to do more to this vector than just turn it into my velocity. Instead, what I'm going to do here is I'm going to go one step further, and I'm going to divide it by its length, and that's going to give us a unit vector, which means its length is 1. We use unit vectors in geometry to refer or designate directions without having any magnitude or length. The magnitude will be fixed to 1. But now if I've removed all of the magnitude out of this so that it's only direction, so sometimes we might draw that like this, it's shorter, it's of length 1, this might be of length 1 here, then we still want to know how much am I attracted to this entity, and especially in the case where I might be attracted to more than one entity, I want to know what the magnitude of my attraction is. And this is where I'm going to bring in a little bit of physics. In normal physics, our attraction, so say with gravity or electromagnetism, our attraction to another entity drops off with the distance. So we might say something like this: our attraction should be divided by the distance, because as our distance gets greater, our attraction gets smaller. But in fact, when we go and measure this in physics and in the real world, we find that electromagnetic attraction and gravitational attraction actually diminishes with the distance squared. And so it's this idea that I'm going to bring into our physics and our geometry as well, that by making our forces of attraction and repulsion be proportional to the distance squared between our two entities, we can sort of fake or simulate real world physics. Now, we still have to decide what our force of attraction is, how strong our attraction is, and this is where in the real world we have gravitational constants that tell us, for instance, how strong the force of attraction of gravity is, or our electromagnetic constants. Well, in your game, in your simulation, you can just make this up, call it 100 or 1,000 or whatever, and it doesn't really matter. If you change it, you might get a gravity that's greater or a gravity that's less than, say, Earth. But when you're working on a video game, usually you can't tell how closely that's going to be. Sometimes you can. It might say, hey, this jump really lasts a long time. It's like I'm jumping on the moon. But all we really need here is some of the physics to make it feel like it's a real simulation. So I had to decide how I was going to build this into my game in terms of rules. And what I decided was I'm going to have some very, very simple rules of attraction and repulsion, which is the entity that is it, that entity will be attracted to every other entity that it can see. So I have built in a visual radius, and I'll mention this here in a second. It can be attracted to every other entity that it can see. And so that's what this first bit of my loop here. Right now I'm inside my collision detection loop. Sorry, right here. I'm inside my loop where I'm looping through all my entities, and I'm checking to see if I've collided. Now up above here, I was checking to see if I collided directly with that entity, but now what I've done here is I've done something completely different. I've said, again, I want to use collide, but instead of passing in the other entity, just itself, ent, I'm passing in that entity with a different radius. Instead, I'm passing it in with my visual radius. What that does is it ends up creating that circle around the entity, the enemy, and then making it larger. And now what I'm saying is if that larger circle collides with me, I can see you. And then I want to do something. Let's go back and take a quick look here. So I can turn on the visual radius by clicking on this, and this will just draw the visual radius. And now we can see the radius around each of my entities. Now, what this is saying is that my red entity, it, will only chase after any of the white entities that it can see within its larger red circle. Likewise, I've given a smaller visual radius for the white circles, and they will only run away from the red circle if they can see it. And so as you can see, otherwise they will just follow their normal path. I'm going to do something here. I'm going to turn up my friction. That means ones that are not trying to run away or flee will slow down with the friction. So you can see some of the other entities have slowed down. But when the red entity enters into their white visual radius, they will start to run away. Okay. Likewise, our red entity will chase them once it reaches into its red visual radius. Now again, the red entity is trying to chase all of them, so that's why it's got a little bit of bizarre behavior. All right, now let's just take a closer look here at the code and how I've implemented this. And what we can see is that, again, as I started off to describe that, first we're only going to do this block of code if you collide with my visual radius. If you collide with my visual radius, then I either want to accelerate towards you if I'm it, or away from you if I'm not it. So my first block here is if I am it, then I want to accelerate towards you. acceleration, say, due to gravity or electromagnetic force, here we have to come up with some constant and decide what it's going to be. Now, we're also going to divide out, as you can see here, by the distance squared. So here I'm squaring the distance so that that acceleration vector is stronger when it's closer and weaker when we're further away. Now let's do a quick check and see what is this dot acceleration. So you can see here, I've got this dot acceleration set to 1 million in this simulation. Now the reason I've got it set to 1 million is because we go ahead and divide by the distance twice. So say the distance between two entities is, let's say, I don't know, 100, then dividing by this twice would be dividing by 10,000. So by setting it to 1 million, that ensures that the amount of acceleration we've got here is still some value or some factor that allows us to speed up. We can actually fiddle with this or change this if we like, and this will change how quickly we accelerate or decelerate away or towards our other entities. Now, the only difference I've got between these two blocks is this logic. How do we apply it? By doing a plus equals to our velocity, that's applying a force of attraction, but by doing a minus equals, that's applying a force of repulsion, sorry, and that's going to force us away. And so in this case, when the other entity is it, then I want to run away. And so that's the force of repulsion that I've got here. Now, you can go ahead and play with this yourself. Since I've got the code available for you, you can go and try it and play, for instance, with our sliders, where we can change our visual radius. Maybe I will turn my visual radius on first, and then we can start changing that visual radius. So maybe make it so that the agent who's it can't see very far. Is kind of blind, works in the dark, everyone else can see better, but because he still moves faster, it looks like he still has some advantage. We can turn up the visual radius of our other ones, maybe slow down, speed up, add some friction. Go ahead and play with it and see how that affects the behavior of the different entities. Now again, even though this looks like it might be actual agents playing a game of tag, this is really just a simulation of particles following physics-like behaviors. So sometimes we will call this a physical system or a physics simulator. All right, this video was intended to help us understand how forces of attraction and repulsion can be added to our game and used to simulate some interesting behavior. So thanks a lot for watching, and we'll see you in the next video.